You are kneeling in an excavation trench. The heat sits low over the dirt. Your trowel has just scraped through a band of compacted sediment to expose something pale and curved. You trade the trowel for a brush. The dust comes away in small yellow clouds. First, you see the polished cross-section where the bone broke, smooth as a worked surface, then the round edge of a hole, then the dark wedge of stone still seated inside the bone. That shoulder blade was not having a good day. To put it mildly, that dark wedge did not fall into the trench by accident. It arrived at speed. It tore through hide and muscle, and stopped only when it met hard tissue. How did an arrow made of stone manage that? By the end of this video, you will never look at a Stone Age arrow the same way again. A shoulder blade with a stone tooth. A cave in South Africa, where tiny stone points appear 64,000 years ago. A surgical knife made of volcano glass. A fresh carcass hit by a stone-tipped dart at full speed. Keep those 4 pictures in your head because each one is coming back later. The standard story is simple, and you have heard it 100 times. Stone Age arrows had tips chipped out of rock. The rock was blunt by modern standards. An arrow only became truly dangerous when someone added metal or poison to the recipe. In that version, prehistoric weapons are a prototype, a rough draft waiting for bronze. The phrase Stone Age quietly becomes a synonym for not very dangerous. The problem with that story is that it confuses 2 different questions. Did people in the Stone Age have metal? Number, did that mean their weapons were crude? That is a completely different question, and it is the one the evidence keeps answering with a no. Start with the material. Flint and obsidian are both brittle, which sounds like a flaw. Brittleness is exactly what lets a napper strike off a flake with a curved edge that ends in a line almost too thin to see. Obsidian is volcanic glass. Lava cools so fast that crystals never get a chance to form, so the result has no internal grain. Steel has a crystal structure. Glass does not. That is why a well-struck obsidian edge looks smooth, even under an electron microscope. A steel scalpel edge, at the same magnification, looks rough and jagged. The material you are picturing as crude out performs the material you are picturing as modern. People figured this out thousands of years ago. Around 2,500 years ago, Mesoamerican artisans were making long prismatic blades out of obsidian, blades with edges so fine that later researchers had to rebuild the technique from scratch just to study them. For centuries, nobody practiced the method. In the 20th century, an archaeologist named Don Crabtree spent years rebuilding it. The revival quickly left the museum. Surgeons started asking whether ancient glass could outperform the steel blades they were cutting with every day. Nobody pulled those edges out of a rock by luck. That is a skill. This is a craft with a chain of decisions, where the first blow lands, how hard it lands, which angle tips the next flake free. Flint and obsidian break with a conchoidal fracture. A ripple pattern spreads from the point of impact, and a skilled hand can read it the way you read the grain in a plank of wood. Set the strike wrong and you lose the whole nodule. Set it right, and you hold a blade with an edge that catches the light and disappears. You are looking at the same skill you meet in good carpentry, just aimed at a different material and applied to a much older problem. Part of that skill was knowing which stone to carry. Flint comes in many grades, from coarse material to fine-grained stone that behaves almost like glass. Obsidian was rarer and more fragile, so people carried it as a premium material, traded it over long distances, and saved it for edges that had to cut. A Mesoamerican workshop could work a core down into a row of prismatic blades, each one with an edge you would not test with a finger. A good core could yield a long series before it was spent. The trade in that glass moved across whole regions, and the blades ended up far from the volcano that produced them. The question did not stay in the museum. A surgeon named Buck published an article called Ancient Technology in Contemporary Surgery in the Western Journal of Medicine in 1982. The article reported that obsidian blades in experimental microsurgery could be infinitely sharper than a honed steel edge. Cuts from the glass held equal or greater tensile strength after 14 days. The blades did not flake. They did not trigger a foreign body reaction. Microsurgery with volcanic glass. Not a fantasy, not a stunt, a published case. A few years later, plastic surgeons ran a controlled version on 40 rats. They made parallel incisions on the same animals, one with an obsidian scalpel and one with a stainless steel scalpel. The obsidian wounds healed with significantly narrower scars at 7, 10, and 14 days. And by day 21, the two sides had converged. Fewer inflammatory cells and less granulation tissue appeared in the obsidian wounds at day 7. On a wound-healing scoreboard, stone beat steel for 2 weeks straight. Before you conclude that this is a video about surgery, hold that detail. A knife point matters, because an arrow tip is a blade delivered by force. A scalpel never leaves a hand. An arrowhead is the same kind of edge carried across open ground at a speed your brain struggles to track. Sharpness is half the story. The other half is what happens when a sharp thing hits a living body. So the real question is not whether stone can be sharp. The real question is how long people have been loading that sharpness into projectiles. Researchers working in the Ethiopian Rift have argued that stone-tipped projectiles go back more than 279,000 years. That predates almost everything you pictured when you thought primitive. At a site called Gadamotta, stone points carry damage that looks like projectile impact. Yonatan Sali led the team that published that argument in 2013. These were probably spears rather than arrows, but the principle was already in place. Attach a cutting edge to something that flies. The bow came later, and its early history hides inside a cave. At Sibadu Cave in South Africa, archaeologists found small stone points. The layers date to around 64,000 years ago. Marlies Lombard and Laurel Philipson proposed in 2010 that some of those points were small enough and shaped well enough to have armed arrows. The word proposed is doing real work there, because the evidence is strong but indirect. Even so, that cave sits halfway back to the beginning of our species, and it suggests that the bow and the stone-tipped arrow are not late inventions. They are old enough to be part of the original equipment. But why would anyone point at small stones and propose a bow? Archaeologists do not call a rock an arrowhead just because it looks pointy. They look for the package, impact damage, edge wear, a shape that could fit a shaft, weight and balance that could fly. When Lombard and Philipson argued for bows, they were reading all of those clues together. Not one pretty stone. That matters more than you think. The early dates are more impressive because the evidence had to pass a stricter test than, that looks like an arrow. Timeline alone does not settle the real question, though. What happens when one of those points actually hits something? To answer that, you need experiments. And people have been running exactly those experiments. A 2020 study by Jay Sitton, Brett Story, Briggs Buchanan, and Metaneron tested 14 different stone-tipped projectile types. Under controlled conditions, they measured how deep each type penetrated a target. Then they compared the results against the geometry of the tip. The pattern was clean, smaller cross-section, and smaller perimeter predicted deeper penetration. Perimeter was the stronger predictor. A slim, sharp stone point does not behave like a club. It behaves like a needle. Then Devin Pettigrew and colleagues took the experiments out of the lab in 2023. Skilled users threw stone-tipped atlatl darts and shot stone-tipped arrows at fresh carcasses. High-speed cameras and a radar gun tracked the impacts. Fine-grained stone produced sharper armatures. Those sharper armatures dramatically improved penetration. Bigger points on bigger shafts carried more energy into the target. The team called the work exploratory. They were right to be careful. But the direction was consistent. A well-made stone point does not bounce off meat. It keeps going. The high-speed footage shows what a museum shelf cannot. A point in a case looks passive. In flight, it has one job. The job is to get all the way in. Motion is part of the weapon. The users mattered as much as the cameras. Pettigrew's team chose skilled volunteers, people whose arms could repeat a throw, and that wrinkle is the point. Real motion wobbles, flexes, and varies, and the stone point still won. You can already see where this is heading: sharp edges, long history, deep penetration. Put those together, and you get something that can open a body from the front while the shooter stands out of reach. And that is before you add the most important layer, what the wound does afterward. The most unsettling evidence does not come from targets, though. It comes from skeletons. In the 1960s, salvage crews working on the banks of the Nile uncovered a cemetery at a site called Jebel Sahaba. 61 individuals came out of the ground, along with a scattering of stone artifacts, and the first analysis counted a number of wounds. Then, the bones went into boxes. For decades, the collection mostly sat there with the old labels still on. You can almost hear the cabinet close. Isabel Krivakoa and colleagues came back to the collection in 2021 with fresh eyes and microscopes. They documented more than 100 lesions that earlier work had missed. Some were lithic fragments still stuck inside bone. Most of the trauma came from projectile weapons. Some wounds had healed, some had not. About a quarter of the injured skeletons showed both healed and unhealed injuries, which is a terrible biography in 2 words. They got hurt, recovered, and then got hurt again. The researchers described Jebel Sahaba not as one massacre frozen in time, but as a place where violence kept coming back. Pause on what that reanalysis means. Researchers studied the bones in the 1960s. They published the results, packed the boxes, and called the case closed. The same boxes later gave up more than 100 wounds nobody had catalogued, including stone fragments that had stayed inside bone for roughly 13,000 years. A stone point did that. It cut through skin, muscle, and connective tissue, and in several cases it did not come out again. The word arrow deserves a moment of caution here. Jebel Sahaba holds evidence of projectile weapons, and archaeologists describe the embedded pieces as lithic fragments, rather than always identifying them as arrowheads. Spears and darts could leave the same signature, but that caution cuts both ways. Whatever launched those fragments, stone was moving fast enough to lodge in human bone. And that is exactly the mechanism the experiments measure. Another burial adds a different angle. At Rapero Tagliente, a rock shelter in northern Italy, archaeologists found the skeleton of a man known as Tagliente I, dating to roughly 17,000 to 15,500 years ago. In 2025, Vitale Sparacello and colleagues reported projectile impact marks on the femur and shin bone, arriving from different directions, with one mark sitting close to the femoral artery. That matters on a living body. A wound near the femoral artery bleeds into the thigh faster than anyone can stop it. The wounds show no sign of healing. Something struck that body hard enough to leave a permanent signature in the skeleton, and the striking object carried stone technology behind it. Now the full picture starts to form, and it rearranges the standard story. The Stone Age arrow was not a blunt stone chip. It was a precision projectile, a razor edge, an efficient cross-section, a shaft built to fly, and enough energy at the tip to push through hide and muscle into bone. Remove any of those ingredients and the arrow becomes a stick with an idea. Keep all of them, and you get the shoulder blade from the opening scene. Think about the arrow as a machine with 4 jobs. The point opens the wound, the shaft carries energy and keeps the tip pointed forward. The fletching steadies the flight. The bow stores the work of your arm and releases it in a fraction of a second. Miss any one job and the whole system tumbles wide of the target, a sharp rock going nowhere. You can make the sharpest point on Earth. If the shaft bends, the point misses. If the fletching is wrong, the arrow wobbles. If the draw is weak, the point bounces. A working arrow solved all 4 problems at once. Solving 4 problems at once is engineering plain and stubborn. The bow itself deserves the same respect. The limb stores energy while you draw. The string hands that energy to the shaft. The shaft has to flex, recover, and fly straight. The fletching keeps the point from tumbling. The hafting has to hold the point absolutely square. One weak joint ends the whole shot. Stone points were bound to shafts with resin, sinew, and cord. A joint that had to survive the launch and the impact. A point that flies sideways still cuts, but it cuts like a thrown pebble. The geometry of the head only matters once the shaft does its job. Reconstruct that whole chain and you are building a machine out of materials gathered from a hillside. And every link has to work or the sharp stone becomes a falling stick. The experiments with fresh carcasses test the end of that chain. That is why the deep penetration looks so strange to watch. The whole system is doing what it was designed to do. Knapping is not smashing rocks until one looks pointy. The maker has to control the angle of every strike, read the grain of the stone, manage the striking platform, and finish with a tip that will not shatter on impact. Key and Lyset ran a large cutting experiment in 2017. The size and shape of a stone tool measurably change its cutting efficiency. A later team quantified edge sharpness on stone flakes from Olduvai Gorge. The word engineering fits those hands better than the word crude ever did. Here is the quietest part of the material evidence. The Olduvai flakes measured in the 2024 study were not sculpted arrowheads. They were simple struck flakes, the kind of thing a person could knock out in a minute. Mechanical testing still found edges sharp enough to quantify. If plain flakes from a site famous for the earliest named stone tools could cut like that, imagine what a maker could do after hundreds of thousands of years of practice on projectile points. The arrowhead is not the first chapter of that story. It is a refined later one. The aside I promised myself I would include. There is no good English word for the sound. An arrow makes on release. Thwip is wrong, too soft. Zip is wrong, too mechanical. I have spent more minutes than I want to admit on this exact problem, and I am no closer anyway. Back to the important part. What makes a wound lethal is never just depth. Blood loss matters. Shock matters. Shock matters. So does the specific organ hit. A sharp edge makes every one of those outcomes more likely. A stone point that opens a wide, ragged channel in muscle can pour blood into tissue faster than the body can close the wound. A point that reaches a major vessel does not need poison. The body supplies its own. The clock starts immediately. That is wound ballistics in one sentence. A small, sharp thing, moving fast, creates a wound channel that can do damage far beyond the visible cut. An arrow wound is also an open channel from the outside into a body that cannot seal it. The shaft comes out, or the shaft stays. Either way, dirt, hair, and stone fragments ride along. Infection follows. Before antibiotics, infection had its own timeline. It did not need a poison recipe. Infection had millennia to win before anyone understood what it was. Some healed injuries in the bones mean someone survived that whole sequence. The unhealed ones mean the sequence won. Even the fragility of stone becomes a feature. A well-made point can break on impact. When a tip breaks off inside a body, the fragment stays there. Archaeologists find exactly that. Lithic pieces embedded in bone. Sometimes the tip, sometimes a fragment of the edge. The arrow did its job and then kept working as a foreign body, stuck where no one could easily remove it. So the arrow was not a failure of technology. It was technology optimized for the materials at hand. No metal meant nobody could cast a bronze head, but a napper could still make a razor edge by learning to read a rock. That is not a small skill. It is a transferable, testable, repeatable piece of engineering, and it stayed effective for tens of thousands of years, longer than any metal arrowhead has managed so far. Look back at the opening scene with all of this in place. That polished break on the scapula, the round hole, the dark point still seated in the bone. The arrow did not fall apart on impact. It did the one thing an arrow does. It went in and it stayed. Every time you walk past a museum case of small flint points, the little triangles lined up in foam, pause for a second. Those are not failed attempts at spears. They are finished weapons. They are the surviving parts of a weapon system. It predates writing, cities, and bronze. People kept manufacturing it for longer than any metal equivalent has existed. What survived inside the stone is not simple violence. Violence appears in every era. What survived is knowledge how to break a rock so it cuts, how to build a shaft so it flies, how to aim a little bit of sharpness across a stretch of open ground. The arrow is a record of that knowledge, written in a material that never needed a furnace. And that is why the word primitive does so much damage. It makes you see a dull thing that happened to work. The people who made these arrows saw a sharp thing that happened to work beautifully, and they spent thousands of generations making it sharper, straighter, and more reliable. Same object, two very different minds looking at it. Maybe the honest ending is a question. The next time someone calls the Stone Age crude, ask them what they mean. Crude compared to what? Compared to a world without metal, or compared to a world where nobody had ever thought of putting a razor on a flying stick? Those are not the same question. The arrow was never crude. And when that polished shoulder blade comes back into view, the dart point still seated in the bone, you will already know the answer. Compared to what? Indeed.